So last time we talked quite a bit about filters and how some of them are used and things like that. I want to get into more of the quantitative information today. I think we left off with a bandpass filter like I have shown here last time. And we talked about the resonant frequency. That was where hopefully the ratio of the output over the input was equal to 1. And that was our resonant frequency, omega naught, and we talked about how to calculate that omega naught is equal to 1 over the square root of LC, right? Remember that from last time? I think that's what we had. And then I talked about this point here. I think we didn't do it in much detail, but as we were finishing up, there's a point across here where we take this 1 and we divide it by the square root of 2, and those are where our half-power frequencies are. So we have this these points here, omega 1 and omega 2. And sometimes they're called omega low and omega high. Okay, those are half-power frequency. And we could find a lot of these on a band pass or a band reject and whatnot. When you do lab this week, you'll be doing a band reject, I believe. But it's probably a little easier to think about it on this band pass filter. So this omega naught, this is the resonant frequency. And incidentally, the calculation of omega naught, this works whether you have parallel or series range. Parallel or series. And I would encourage you to maybe take a 3x5 index card and start to put the relationships that work for series circuits, because there'll be some of them that we get into that just work for series. There'll be some of them that just work for parallel. Put parallel on one side and series on the other side. And I'd encourage you to bring that to the final. So that would be a useful tool. Well, let's talk about the calculation of some of these. And again, we could talk about omega 1 and omega 2. And that's equal to omega naught, the resonant frequency, times this factor, be minus and then plus 1 over 2q plus the square root of 1 over 2q squared plus 1. Oops. I don't want that kind of a bracket. Okay. So if you want to you find the omega 1, you'll use the negative sign. If you want to find the omega 2, you'll use the positive sign. So that's what that's meant. The other thing that we have to deal with, and this is also good for parallel and series. You can use this for parallel and series both. The other thing that we need to deal with is the quality. That's what Q is. So Q is defined as the quality, which we could say was 2 pi times the maximum energy stored divided by the total energy dissipated. Okay, and while that defines quality, I don't know that I've ever calculated quality using that. We have some other calculations for quality. One thing that we'll note with quality is it has no units. It's a unitless quantity. Most of the things we'll be talking about will have units of radians per second. These are all radians, radians per second. Omega naught, omega 1, omega 2, but quality has no units, as you can see from the calculation. Well, how do you calculate quality? Well, if you have this is one that really varies whether you have a series circuit or whether you have a parallel circuit. And I'm not going to go through the development of these equations. Your author in chapter 14 does a nice job of that. I'm just going to reproduce them here. So we could say that the quality in a series circuit would be equal to omega naught, the resonant frequency, times the inductance L divided by the resistance. You'd obviously want to use base units, so don't get tangled up with millihenries or kiloohms. Make sure you use henries and ohms. We could say that this was also equal to 1 divided by omega naught times C times R, all of those in the denominator. And lastly, again for a series circuit, we could say that it was 1 over R times the square root of L over C. And your author does a lot more on developing those. I'm just going to put them down there. Then if we have a parallel circuit, we could say that the quality could be calculated a little bit differently. Omega naught times R times C, or R divided by omega naught times L, or R times the square root of C over L. Okay. So those are ways that you can calculate the quality. And we'll go through an example and calculate some quality so you get an idea of what that's a measure of. Before we do that, I'd like to finish up with a few things here. I might talk about the bandwidth. So this is our bandwidth. So bandwidth, sometimes we'll give it the symbol BW. That's probably not a very good one because I don't like W's floating around because then they start to look like omegas and whatnot. So I think probably a better one is beta. Okay, so I'll draw a beta, B with a tail on it there. So I'll try and use beta for my bandwidth, which would be omega 2 or omega high minus omega 1 or omega low. Okay, which we could also say that it was equal to omega naught divided by the quality Q. And this is good again for both series and parallel. So you can see it's lots of little equations. As we work problems, it'd be nice to have, like I mentioned, that index card with a series on one side, parallel on the other. Bandwidth is also radians per second. Okay. The last thing is if I look at the separate calculations for bandwidth for a parallel circuit. For parallel, you can say that the bandwidth is equal to 1 over RC, and then for a series, you could say that the bandwidth beta is equal to R divided by L. So those are some equations that we can look at in terms of describing that wave. In lab, you'll have something, you're going to have a notch. So it'll look something like this. But you'll take this value here and then you'll come down dividing that by the square root of 2 and you'll be able to start to measure some of these quantities, including the bandwidth and things like that. So you get some practical use in that this week. Well, let's try an example using this information. Let's take a circuit here. It looks like we have some sort of a parallel resonance. We've got a current source that's 50 milliamps or 50 cosine omega t in milliamps. Got a 2 k ohm resistor, a 40 millihenry inductor, and a half microfarad capacitor. So again, we have to be pretty careful with the units on those. And what we'd like to find is I'd like to find the resonant frequency for this circuit. When is it at resonance? I'd like to find the quality, and I'd like to find the half power frequencies. Okay, that's what omega 1 and omega 2 are. Those are the half power frequencies. Okay, omega 1 and omega 2 are known as the half power frequencies.
What would the signal actually be if something's operating or if you're getting an output at omega 1 and omega 2?
Well, when you're getting an output at omega 1 and omega 2, it's just an output. I mean, it just happens to be a point on this curve. Yeah, it's just of a reduced value. there's nothing splendid that happens at that particular point. So, well, omega naught's pretty easy, right? Could we do omega naught? For series and parallel, it's just 1 over the square root of LC, right? So I could say that this is 1 divided by the square root of, what am I going to have here? 40 millihenries. So I have to say 40 times 10 to the minus 3. And then C is a half microfarad, so 1/2 times 10 to the minus 6. So when you go through that, it turns out to be 10 to the 4, which is what, 10,000 radians per second. So that'd be our resonant frequency, 10,000 radians per second. So we've got omega naught. What's the next one? Q. Do we have an expression for Q? Let's see. We could say that it was with parallel omega naught RC. How about that one? Seems as good as any. So let's give that a try. Omega naught RC. So we'll say that we just found omega naught, 10,000 radians per second. And then R is 2,000 base units again, and C is a half times 10 to the minus 6, a half microfarad. So this turns out to be equal to 5. There's no units on that. It's a unitless quantity. So that's a quality of 5. Let's see. I don't think we were asked for it, but let's look at the bandwidth. Can I calculate the bandwidth? I should be able to say that that's just omega naught over quality, right? Does that work? Yeah. We saw that one here. Bandwidth is omega naught over the quality. So what do we get for omega naught? We got 10,000 over quality of 5. So our bandwidth is what, 2,000? Now we're back to radians per second. So that'll be kind of interesting. We weren't asked for that one, but that'd be kind of an interesting point. Let's see, do we have everything to calculate omega 1 and omega 2? We've got the quality. Now we're looking for omega 1 and omega 2. Yeah, I think I'm just going to go up here and use this equation for my omega 1 and omega 2. All I need to know is the quality and omega naught to do that, and I have those pieces. So I can say that, I'm going to start that over here, that omega 1 is going to be equal to omega naught times minus 1 over 2q plus the square root of 1 over 2q squared plus 1. So that is 10,000 times minus q is 5, so minus a tenth plus the square root of a tenth squared plus 1, which turns out to be 9,049.88 radians per second. We've got too many significant figures there, but I'm going to play around with that number. I don't want you to think that I'm cheating on you, so I'll leave quite a few decimal places there. So we could say 9,050, but we'll say 9,049.88. Then I can do omega 2. Omega 2 should be equal to omega naught, then plus 1 over 2q plus the square root of 1 over 2q squared plus 1, 10,000 times a positive tenth square root of a tenth squared plus 1. And that gets us 11,000. 49.88, again, radians per second. Okay.
B2 could also be equal to bandwidth plus omega 1.
Yeah, absolutely. Yeah. We could say that, or omega 2 is equal to omega 1 plus the bandwidth. That would work. We can see those numbers. Take that 9,049 and add 2,000 to it. That works out okay. What about, since you posed that question, let's finish up this page here with a question that, well, maybe we'll start a new page here. So, question to continue here. Yes? Should Q be 10? Q is 5, and I think everywhere I multiplied Q by 2. Oh, okay. Well, oh, back when you calculated it? Yeah, maybe I didn't write down the circuit right. Ah, that's what I did. Okay. Let me change things on you a little bit. I think you're absolutely right, but I had done this wrong. This should be a 1/4 microfarad. Which you're absolutely right, but I'm changing this on you. So now if we're at a 1/4, we're at 5.
So it's still the right values if it were half the...
Well, if it were half, they would be right. This was 10. Yes. Yeah, they're right. I'm glad they checked me on that. Have any other problems? I don't think that shows up anywhere. Oops, right here. So a 1/4 times 40 is 10, and then I have 10 minus 3 minus 6. Is that right? Yeah, now we're good. So this one would have been off also. Maybe you saw that one. Okay, so I just fixed the C value there. Questions of that? So let me go on to ask the question that I wanted to pose then. The question came up was that omega 2 is equal to omega 1 plus beta. And that's absolutely right. And then I was going to go a little bit further and say, could we take beta and say that omega 1 and omega 2 is equal to omega naught plus or minus beta over 2. Can you say that? Well, let's see. Looking at our numbers here, what numbers did we have? Omega naught's right at 10,000, isn't it? Okay, so I got omega naught at 10,000, and the bandwidth is 2,000, so that'd be 1,000. So that would put me at, for this, that would put me at what? 9,000 and 11,000, wouldn't it? Something's not right, is it? Okay. Now, it's not a mistake I made. This is the way it's supposed to be. This doesn't work. Okay? Because the simple reason is because omega naught is not the arithmetic average of omega 1 and omega 2. It's not omega 1 plus omega 2 divided by 2. That's absolutely untrue. But rather, omega naught is the geometric average of omega 1 and omega 2. Okay? So normally when we take an average, when we give a test in hand, we take an average, we add up all the scores and divide by the number of scores. Here we added these two up and we divided. That's the arithmetic average. But the geometric average, we would multiply them up and take the square root. Okay? Does that work out? I heard some calculators clicking around there. I think if you multiply omega 1 times omega 2 and take the square root, you'll come up with a correct answer. So that's something to hang on to. Not only is it not the arithmetic average, but it is the geometric average.
So we got the bandwidth was 2,000 meters per second.
Right.
And omega 1 is 9,000.
49. Yeah.
And then
If it was arithmetic, it would be just 9,000.
right. So omega 2 equals omega 1 plus beta.
Yeah, this is fine.
That is correct.
Yeah, there's no problem with that.
Okay.
Yeah, I just don't get to divide beta in half and say that's omega naught. This is okay. Okay, let me ask another question then. So let's say that you want to tighten up the bandwidth. You want to go from 2,000 to 500. So you'd like to try and figure out what value of resistance will produce a bandwidth of 500 radians per second. And we'll say, and we'd like to also find Q at that. Okay. So before, to reiterate what we had, what did we have before? We had a resistance of 2K. We had a quality then of 5 and a bandwidth of 2,000. So now we would like a bandwidth of 500. Let's see if we can make that happen. Well, I know that there's lots of ways to probably do this, but I could say that bandwidth was equal to omega naught over Q. We've already used that. I could say that Q, the quality, is equal to omega naught times R times C. I think we've already used that. So I could say then further that the bandwidth is equal to omega naught divided by omega naught RC. I get to cancel that, so I just have 1 over RC. Is that right? Have I talked about that one? Hey, look at that. Right there. Okay. So we could say then that the resistance is equal to 1 over the bandwidth times the capacitance. So I have 1 divided by the bandwidth. We want 500, so there's 500. And then I have what? A quarter times 10 to the minus 6, a quarter microfarads. That's what I had changed before. So when you hammer out these numbers, this turns out to be 8,000 ohms. Okay. So we had to have a fairly large increase in resistance, which is kind of nice because sometimes when we have series resonance, students will say, hey, if I can get a really great filter if I have 5 ohms of resistance. Well, what do inductors oftentimes have a lot of? Resistance. How about your function generator? Resistance. I mean, I don't know if you've noticed, the function generator says right on the front, it's got 50 ohms of internal resistance. So we take a great design that has maybe 5 ohms of resistance in it, and we throw 500 ohms of inductance resistance. We throw another 50 of function generator. What happens to our great design? It starts to fall apart pretty fast. So this is kind of nice that we reduce our bandwidth by increasing the resistance. So that's kind of a good thing. Just out of curiosity, we went from a quality of 5. What's our quality now? Well, we said that the quality would be, we could say it was omega naught over the bandwidth beta, right there. So we still have the same omega naught, that's worth noting, 10,000, divided by our bandwidth, which is 500, so we get 20. So our quality has increased from 5 to 20, hasn't Questions with that? Well, I'd like to, so I need to keep track of this. This is page 3. And this should be it. So if I look at a typical circuit, a typical parallel circuit, and we'll go through the same argument for series eventually. C, R, and L. And I look into these terminals, and I want to talk about the admittance Y, where of course the admittance 1 over the impedance Z is equal to the admittance. So what's the admittance for this thing going to be? Well, it's going to be equal to 1 over R, and we talked a little bit about this last time we were together, plus J times omega C minus 1 over omega L. And when I got the term in the brackets there to cancel out, when omega C was equal to 1 over omega L, that's where we got our resonant frequency, 1 over the square root of LC. Well, I'd like to go through a variety of steps here. I'll try and go fairly carefully and show the substitution as I go along. We could say then that this admittance would be equal to 1 over R. So I'll try and factor that out. So I'm going to have 1 plus J. So I better have a what? Omega and an R and a C there. Minus R over omega L. Okay. I think if you multiply that through, you'll be okay. You might wonder, well, why we did that, and I hope you'll be patient as we go through this. 1 over R then times 1 plus J. Speaking of wondering why we do this, I think I'll multiply top and bottom by omega naught. So I have omega times omega naught times RC divided by omega naught minus, and again, multiply top and bottom by omega naught. So I'm going to have R omega naught divided by omega times omega naught times L. Okay. Can I just multiply something by omega over omega naught? Yeah, omega over omega naught is 1. You can multiply anything by 1, right? We'll spend most of next term multiplying by these funny looking 1s. But anyway, the reason for doing this is now I can group up this omega naught RC here. That has a special name. We call that Q. And this R over omega naught L, what do you call that? Q also. So I can factor a Q out of this thing and say that I have then 1 over R times 1 plus J Q omega over omega naught minus omega naught over omega. That looks interesting. Okay. And let's see, what could I do with that? I get a common denominator. So I'm say that I have 1 over R times 1 plus J, and maybe we'll write this Q a little differently. Q, remember, that is really what? Omega naught over beta. So I'll say that's omega naught over bandwidth beta. And then if I get a common denominator, this is going to be omega squared minus omega naught squared divided by omega times omega naught. Okay. Difference of 2 squares, right? Yeah, difference of 2 squares. So I could say then that this would be equal to 1 over R times 1 plus J. Then how do I want to do this? I get to cancel this with that, right? And then let's see, the difference of 2 squares. Difference of 2 squares, that's one we always learn in algebra to look for. That would be omega plus omega naught times omega minus omega naught. I think if you multiply that out, you'll get that. So I'm going to write that as omega plus omega naught times omega minus omega naught. divided by, what do I have left? I have that omega there, and I have that bandwidth, and that's why I don't like to say bandwidth is BW. And in fact, I think I'll be really clear here. I'm going to switch the order of this and say omega times beta, just so I don't end up with BW, and then, oh, is that a omega or is that a W? Okay. So that's actually the admittance of that thing. And I'm going to stick with that for now. Okay, this is exact. Okay. So no matter what frequency you're running at, you can get the admittance by putting the admittance in here. You find the resonant frequency, you put the frequency that you're driving it at. So omega naught, that's the resonant frequency, and then let's say that you're going to drive it at something other than the resonant frequency, you'd put that in. Okay. Back at this problem here, the resonant frequency was what? 10,000? Where do we have that? Right here. The resonant frequency was 10,000. So what happens if someone says, well, what happens if you run this at 11,000? Well, we could use this expression. We put 10,000 in for omega naught, and we put 11,000 in for omega. Okay. Now, if we happen to be inside the half-power frequencies, so let's say that we think of this again as a bandpass, and it wouldn't necessarily need to be a bandpass. But omega could be any value, but there is a simplification if we are inside here. So if we're inside the half-power frequencies, so in this region here, we can have some simplification, and we'll tackle another page for that. Let's see. So I can say then, if our frequency that we're going to drive it at is between omega 1 and omega 2, wasn't that what I was describing with this thing? If we're inside what's dictated by the half-power frequencies, omega 1 and omega 2, if we're inside there, we can reduce this. We can get an approximation then that the admittance Y is approximately, it's not exactly, but it's approximately equal to 1 over R times 1 plus J times omega minus omega naught divided by the bandwidth over 2. Okay, 1 plus J, omega minus omega naught, the bandwidth over 2. Which you can see is a lot easier calculation. A lot of times these approximations came from when we didn't have calculators, and if you were doing this by hand or with a slide rule or a piece of scratch paper, this was a welcome relief from this one over here. But you know, with the computers we have nowadays, I'm not sure that this is a big deal. But it's kind of interesting. So this is an approximation. Let's see. I think they're saying, yeah, it's pretty close. That's where you get that bandwidth over 2. I'd have to go through a little more of how they do that. So what we'll do when we get together next time is we're going to take this approximation and this exact one, and we're going to apply it back to this and ask, what is this voltage out here if we're running at 10,500 radians per second? Now this is the circuit that we started with today, exactly the same. I've even corrected this capacitance here. We know from our first work on this that omega was 10,000 radians per second and the bandwidth was 2,000. So we'll go through this calculation with not only the exact form but also the approximation and see how close they are. So that'll be where we start next time we get together. Take care till then. I'll see some of you in lab. Thank you.